This video is meant to go along with the PowerPoint that I put out there for the review for our Chapter 4 test this semester. I'm going to go through a piece at a time and hopefully, not that fast, give you answers for things, for the problems that showed up in there. I couldn't get my pen to write directly on my PowerPoint, so I had to cut and paste, but this should match up pretty much slide for slide with what you saw. On this first example, which of the following is not a function? The key word here is which one is not a function. And to check to see whether or not we have a function, we do the vertical line test. So if we draw vertical lines through A, B, and C, we're successful in all of those. But D is the one that does not pass the vertical line test. This tablet I have is very hard to write on, so I'm sorry that it's going to be sloppy. So it fails the vertical line test. However, if we move on to the idea that we covered in section 4.1, if we're trying to decide whether or not it's one-to-one, that is where we actually draw our horizontal lines. So horizontal lines, perfectly fine through A and B. We already said this one's not a function to begin with, so we don't need to look at it anymore. But C is not one-to-one because our horizontal line touches it in two different places. Anytime we can draw a horizontal line that crosses two or more times, that means it's not one-to-one. So C is the graph that is not a one-to-one function. If we look at F and G, and if we're told that they are inverse functions, then when I take the composition of those two functions, I'm going to get x and only x. Anything else, anything even close to that, is not good enough. If I take the composition of a function with its inverse, I should be left with plain old, regular, boring old x. So B is the answer there. When we're checking to decide whether or not two functions are inverses, there are two approaches we could take. One is to find the composition, as was mentioned on the last slide. And so if I plug G into F, I create a little complex fraction here. And when I simplify and I clean things up, 2 over 1 times the reciprocal, which is x over 2, does in fact leave us with plain old regular x here. So I would say yes, these two functions are inverses of each other. So those two functions are inverses. If we want to find the inverse of a function f of x, remember we start by rewriting f of x as y. And every place there's an x, you put a y, and every place there's a y, you put an x. After that, you solve the new equation for y. That means we're going to multiply both sides of the equation by the denominator, y plus 1. We're going to get to distribute on the left so that we can regroup our terms, getting our terms with the y's in them all on one side of the equal sign. Then we get to factor out the y and divide both sides by 2 minus x. This new expression is the inverse of the function that we started with. And if we check the list that we are given in our multiple choice review, hopefully one of them matches, and it does. Looks like answer D. When we are looking at exponential functions, the domain is the set of numbers that we get to plug in for x, and there's nothing that's going to make that exponential function undefined. So our domain is going to be all real numbers. Our logarithm is where we have to worry about restricted domains. The range, even though we could plug in all real numbers, the only types of numbers that got spit out were the positive ones. I cannot raise a positive number to any power in the world, positive or negative, and get anything other than a positive number. I never actually get 0 itself. I can get very close to 0, but we have an open interval there because exactly 0 is never attained. So if we look at the inverse of those functions, we said the domain of b to the x is all real numbers, and that the range was the set of positive numbers. When we have an inverse of that function, if a function has the inverse, then they just flip-flop. The domain of the inverse is the range of the function that we started with, which means the domain of this inverse function is positive numbers, and that even though it can only accept positive numbers, it's going to spit out all real numbers. So they just switch. The domain of one is the inverse of the other. And it doesn't in any way, shape, or form depend on b, assuming we're within those parameters. So the inverse, the name that we gave to the inverse of b to the x, is log base b of x. Our logarithm function was the inverse of our exponential function. Also, we know that log base b of x equals y if and only if b to the y power is equal to x. The base of our log is the base of our exponential. Our exponent is over here, and b to the y power is equal to this stuff inside. So our approach to a problem like this one, when it says evaluate without using a calculator, is we need to remember the rule or the fact that log base b of b to the r power is going to be equal to r all the time. If these bases match, then our answer is just the exponent. So if I can write log base 2 of 1 over square root of 2 as log base 2 of 2 to some power, then my answer will be very easy to compute without using my calculator. Now I know a square root means it's raised to the 1/2 power, and if I drop it to the bottom of the fraction, that makes it negative. So log base 2 of 2 to the negative 1/2 power is equal to negative 1/2. Same idea here as 2 slides ago. If we want to look at exponential form of our logarithmic expression, here is the base of our expression. The exponent is over here, and x to the 4th power is going to be 1 over 16. If I recognize the fact that 1/16 is 1/2 to the 4th power, then I can match my bases and say that x has to be equal to 1/2. On these 2 slides, expand the following right as a single log expression. These 2 didn't have anything on the slides, but be sure you review your rules when you multiply expressions, when you bring exponents down, when do you divide them, that sort of thing, and be able to split them apart and put them back together. I can try to show some more of those if you have questions on those later on. When we have an equation with an exponential function in it, and we can't write both sides as powers of the same base, our first step is to get the exponential term by itself by getting rid of anything extra. So add or subtract anything that might be added to or subtracted from it. Multiply or divide any coefficients out. You can reduce this if you'd like, or in this case our calculator doesn't care, so we don't have to. Then we're going to take the log of both sides. And the reason we do that is so that we can use those properties to get that exponent down to the ground where we need it to be so we can solve for x. Now when we are using e, we're going to use our natural log instead of our common log. Our calculator only understands common logs and natural logs, and we like natural log here for the reason that we just used back here on this slide. If I can get to it. That one. Natural log means log base e. So if I have log base e of e to some power, then my answer is just that power. Where am I? So natural log of e to the 0.05x is just going to leave behind 0.05x. Then our last step in the problem is to divide both sides by 0.05. And then we can round to whatever accuracy we feel like we should round to. So natural log of 12/10. I want to divide that by 0.05. We get 3.6464 blah 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 blah. So we will call that 3.46 for now. If you have questions about any of these problems or any of the topics that either are covered in this video or not, send me an email, get a hold of me, and we can work through some more problems together.